The 2016 Kavli Prize in Astrophysics is awarded to Ron Drever, Kip Thorne, and Ray Weiss for the direct detection of gravitational waves. It is a great pleasure for me as chair of the prize committee to introduce the laureates. Ron Drever was born in Scotland, studied at Glasgow University, where he got his PhD in 1958. At Glasgow, he looked for gravitational waves first by monitoring the vibrations of aluminum bar detectors, and then by setting up a 10-meter interferometer. In 1979, he was hired by the California Institute of Technology to lead a new program in experimental gravitation, which led to the construction of a 40-meter device that tested many of the techniques employed in Ligo. Unfortunately, Ron Drever, due to ill health, cannot be with us today. Kip Thorne was born in Utah and studied physics at the California Institute of Technology. After obtaining his PhD from Princeton University in 1965 and carrying out 2 years of postdoctoral study, he returned to Caltech and has worked there ever since. Thorne has carried out a wide range of theoretical research in gravitation and astrophysics. His work has also provided the theoretical underpinnings for LIGO. He and his colleagues have carried out numerical simulations of the kind that allowed the September 2015 event to be identified as a pair of merging black holes. Born in Berlin, Ray Weiss obtained his PhD from the Massachusetts Institute of Technology. After serving as an assistant professor of physics at Tufts University and then a research associate at Princeton, he returned to MIT and has been there ever since. Weiss has contributed to a variety of scientific fields, including atomic physics, laser physics, and astronomy. As part of the latter, he was one of the founders of NASA's COBE cosmic microwave mission. He co-founded LIGO with Thorne and later Drever, having laid the foundations for the project in 1972 with a paper detailing how an interferometer could distinguish gravitational waves from background noise. He has continued to contribute to nearly all elements of the experiment since then. Kip Thorne and Ray Weiss will give their lecture together, entitled Probing the Universe with Gravitational Waves. And it will be possible to ask questions after the lecture. So, please.
Thank you. I guess we have to get this thing up on the screen, if we can do that. Maybe before I start, I'd like to say something that, first of all, I think Kip and I are extremely honored to be here. It's very kind of you to do this, to have a prize for us like this. But the other thing is we are actually a symbol of something much larger than the two of us. We are a symbol of 1,000 people who have been involved in this experiment. And it's hard to see that come out in us because we're just two. And I think when you look in detail how this project worked, you'll find out that many of the others had extremely significant parts in it. So think of it as we are symbols of that, not that's just us. Anyway, the title of our talk is Probing the Universe with Gravitational Waves. And before I really start, let me say a little bit about the epoch we're in. About 100 years ago, this was mentioned already yesterday, Einstein came up with this new theory of gravitation called general relativity. And it's very interesting, and it's also wonderful that within that 100 years, we actually showed that there was gravitational radiation, gravitational waves in a very direct measurement. Had already been shown earlier, we'll talk a little bit about that, but not in this very direct fashion. And I'd like to start by giving you a little feel for what the theory is like. In other words, what's different about Einstein than Newton, the thing that you learned in high school and college probably? What's different about it is that he had already done special relativity and already had gotten into the regime where you had to think about how you measure things in 4 dimensions, really. You had to include time as one of the variables. And what you're seeing here is a visualization of the following idea. Namely, think of the following. What you see in the middle there is the sun, and to the right, there's the sun, and to the right here is the Earth. We'll talk about these dimples in a second. But what you have to visualize is first how you would lay out in the new way of thinking of gravity. It's no longer a force. It's a distortion of the geometry. And the way you want to think about it is get the sun and the Earth away from there, and lay out space with a meter stick, and wherever you see an intersection of lines, you had 2 meter sticks that you put together, and you measured out the space, and you left the space at each intersection with a clock. Everywhere there's a clock, and those clocks were all synchronized. Okay, so can you imagine that? Just imagine this network of meter sticks and clocks everywhere. And now what happens, you place the sun in that collection of you measuring the space, and it has made a distortion in the space. And that's this distortion. And then over here is the Earth, and it's made a little distortion as well. And what goes on now is no longer thinking about it as the Earth is pulling on the sun is pulling on the Earth, but rather that the distortion of space is the thing that directs the motion of the Earth around the sun. That's the way to think about it. And this same theory then led to something which was new. And what was the idea that there should be gravitational communication. You no longer could have things moving at the speed of infinite speeds. Information, even in gravitation, had to travel with some finite speed. And we now think it's the velocity of light. And that's what this is what I want to show you is next in this network. There is now, I'll show you a gravitational wave. You'll see this, it'll move, and I'll describe it. Don't get sick of looking at it. I went the wrong way, excuse me. But can you, yeah, okay. What you're seeing is the following. And don't get mesmerized by this. You're at this red spot right there, and what is coming at you, or going into the screen, is a gravitational wave moving at the velocity of light. And what it's doing is it's stretching space in one dimension while it's contracting space in the other dimension that's perpendicular to it. All the dirty work that the gravitational wave does is transverse to the motion of the wave. And now, if you get some image of what's going on here, you'll see there's something constant in this picture. It's not obvious until you get shown this thing. It turns out the thing that's constant in this picture is the strain. In other words, it's the change in separation. Here, look, it's moving a little bit, that point right there. It's moving, and so is one over here, and they're moving. And the amount they move is proportional to their separation to begin with. So the change in space divided by the separation is a constant, and that's called the strain. And we call that h, and you'll see h written in many of the slides, okay? So that, now you've gotten good sick, let's look at something that you don't get so much motion in. And here is sort of the beginning of, this is Einstein's 1916 paper. That's not the one that was celebrated in just last year. That was the origin of the whole theory. In 1916, he wrote a paper applying the theory. And that's where gravitational waves first appeared. And in that paper, when he gets to it, he's done, pretty much showed you that diagram I just showed you. He says in German, you can read it underlined, but in English, it says that after he gets done, this is an expression for how much energy is carried away by a gravitational wave. And he says, in any case one can think of, A, which is that quantity, which is talking about the energy that's being carried away, will have practically a vanishing value. He says right out in the first paper, this is impossible to do, you can't measure it. And then people have been looking for evidence for this in his papers, and we can't find them. I mean, but there's some sort of back-of-the-envelope calculation somewhere in Einstein's papers, which I hope people will find, and I made this up. I mean, he might have considered what would happen at the gravitational radiation that comes from 2 trains colliding with each other. For example, that's something that in his technology he might have known about. And here is a formula that comes out of that theory, and that calculates h for you if you know the following. You have Newton's constant, the mass of the train, the velocity squared of that train, and this is the distance you're away from it, and this is the velocity of light to the 4th power, as you can see, c squared times c squared. That whole quantity is dimensionless, and that's h. That is the strain that you would predict. So, and you can see if you put some numbers into this, you assume a train of 10 to the 5 kilograms and a velocity which a train might have had in those days of 100 kilometers per hour. And the collision takes only 1/3 of a second, let's say, to make a mess like that. And then you have to be in a way far enough away from it so you're in a radiation zone. You're in a zone where you actually see the radiation. You're not just seeing the near field of that, the attraction, the Newtonian attraction. He will get an h that is really quite small, 10 to the minus 42. And Einstein quite right to say that'll never have an impact on anything. It's tiny. Okay? Later on, we'll see what we discovered was 10 to the minus 21, which is bad enough. Okay? But this is really hopeless. So, so then he might have done this kind of calculation. People knew already about binary stars. They knew that they didn't know about the galaxy that well, but they knew they were close to us. There were some number of tens or ones light years away. And so he might have thought about it this way. Could you find a binary star system that changes its aspect as it lives because it's radiating gravitational waves away? And so he might have considered something with a solar mass. That's the mass of the sun, 2 objects. The period of it would be 1 day. These go around each other once a day. Well, okay, this is 10, it's the center of our galaxy. And you calculate for that an h value, which is 10 to the minus 23. That's not so hopeless, you'll see as we get along. It's bad, but not hopeless. But this period is terrible. But if you wanted to do it in his day, you would have had to look at it. And how long would it take before you saw these things get closer together? It would have taken something perceptible, about 10 to the 13 years. So longer than, they didn't know this at the time, but longer than the age of the universe. So you can't go looking with a telescope and see the gravitational radiation in Einstein's day. So 100 years later, other things have happened. And the first people and they actually won the Nobel Prize for this. These are the people who first saw evidence of gravitational waves with a system very much like the one I just described to you, but one which had much more interesting masses. Well, interesting is not the right word. Smaller mass, they were tiny little masses, neutron stars, and these have the mass of the sun, but they're only about the size of Oslo. Okay? And they go around each other. And this is, I will talk about them. And the 2 people who discovered this by radio astronomy was Russell Hultz, who was a graduate student, and Joe Taylor, and he's the professor who was his mentor. And what they saw was this. They saw nothing because they did a radio telescope, but they saw the pulses, 17 of them per second, coming from this pulsar. This is one of these neutron stars. And what they watched it, they listened to it, however you want to, and they didn't know it was a partner to another neutron star. They evolved that idea by watching this for a while, listening to it for a while. And they saw it wasn't regular. It was sometimes going the rate was going a little faster, sometimes a little slower. And so by doing this, they divined the fact that there was another star going around. So this system is an orbiting system, just like what Einstein might have imagined, but it's going a hell of a lot faster. And they had a lovely clock in this thing. And so they plotted something which is really quite dramatic. This is one of the most amazing pictures in astronomy. So they plotted the time. Every time this goes around, they registered. Okay, they could see this listen to it in the rate of emission by that star, and they plotted the time it took around. And each time it went around, here's the years they spent time doing it from about 1973. They kept on doing it, but this picture ends at about 2000. And they saw this. These are the points they put into this picture, and what they noticed is that it kept coming sooner. The period made the thing change. The period changed. It changed, and it got a little shorter every time it went around. And so here is a plot of how much shorter. This is the time it took. And it always was, this is negative. So they're losing time. Time gets faster as these things go around. And this is a curve that you would have gotten out of Einstein's theory, or they did get out of Einstein's theory that was developed in 1915. And it's not a fit. This is dead on. And they saw this acceleration of the orbit. And they only could ascribe that to that there was somehow the system was losing energy, and it was losing energy at a rate that was just exactly what you would predict if it was gravitational waves. So that was the really first observation, very central to us too, because it told us about some sources that we knew we might be able to do and see if we were going to look directly at them. So now here is the piece of the story that is more hard, more difficult. Here's where the experimenters get into it. The theorists predict numbers for such a thing, and it's strange that theorists would predict when they look at the astrophysical setting of these things is about, for us, for things that we might see on the ground, and we'll talk more about that in a minute, this is a strain. It's a change in length divided by a length. There's that h. And it's about less than 10 to the minus 21. And to most people, that's a number that's really so small. When you think of experiments, when you do an experiment to 1%, you're doing it to 10 minus 2, right? So this is something you're doing to unbelievable precision so that you can see this effect. Well, that was a requirement. And if you have a system, which we'll be talking about in a minute, which is 4 kilometers big, like Ligo and the other detectors are, the endpoints of that system will move by 4 times 10 to the minus 18 meters. Now, let's try to interpret what that is. And, many of you do know, but let's talk about it. And so here's a meter, that's a meter. Okay, well, everybody knows a meter. And here's something for Americans, 40 inches, okay? And so well, let's divide it by 10,000, so you get down to the hair. Your hair is about 10,000th of a meter. Remember, you're going down to 10 to the minus 18. So you've got to go a lot further than that. And a wavelength of light is another. You divide that by another 100, and you get down to about a micron, 1/1,000,000th of a meter. And that's about the wavelength of light, and still very perceptible to you. I mean, all of us can experience that by just looking looking between your fingers and seeing interference fringes at a mercury light or something like that. And you can even experience the next factor of 10,000, which is the size of an atom. And you can do that by looking at an oil film on water, if you thought about it a little bit. You drop a drop of oil on the water, know the volume of that, it spreads out, and you can get that. You're talking about a thing that's about a 10 to the minus 10 meters high. That's an experiment you could still do. Even you, even I, all of us. And so then, okay, but now we get into regimes which are not so popular. And now you have to, because you're not there yet, you divide by another 100,000, and you get to about the inside of an atom the size of a nucleus. And we're still not quite there. You have to divide that by 1,000 more, and then you get to 10 to the minus 18 meters. So I don't know if that gives you a feeling for what the sizes are, okay? They're tiny. So here's a gentleman who actually tried to do this. And this is Joseph Weber, who is at the University of Maryland. And he had the idea, and this came out of a meeting in 1957, a sort of a really critical meeting for the whole field of gravity at Chapel Hill, when the theorists, many of the theorists and many famous theorists had gotten together finally and sort of worried. Einstein had worried endlessly about the reality of these waves, and I won't go into the history of that. It's an interesting history. But he himself believed and didn't believe, then believed again. It was one of these things. And what happened is at that meeting, finally people began to agree that yes, it was possible that gravitational waves would carry energy, and they did mechanical things that you could measure. And the idea then that Joe Weber had, along with John Wheeler, was to try to take and see when a gravitational wave would stretch this bar. This is a big piece of aluminum, and he instrumented this bar with a whole bunch of sensors that are along in here, and there he is working on it, and he was hoping to hear that bar, hear the bar. Actually, listen to the bar. And the idea was a gravitational wave would come along, stretch the bar, but in such a rate that it would just, like if you went with a hammer and hit it. So, boom, it sings along like a xylophone. That was the idea. And so he did that, and to everybody's amazement, in 1969, he published a paper saying that he had several of these bars, and they were, in fact, he had one in Chicago in the United States, one in Maryland, one in a golf course near the campus, and he saw coincidences, all three of the bars, and that was quite significant for him. And, but it turned out, immediately, as soon as that was published, a lot of people, I mean, this is a very dramatic discovery, tried to do exactly the same experiment. And many of them could not, well, all of them could not find anything. And that's one of the mysteries, and what really was Joe Weber looking at. That's the thing you can ask me about in questions if you're interested. There's not yet a very good answer to that. But nevertheless, another idea came along, which actually is the one that Ligo was based on. And that's this, and let me describe a little to you what you're going to see here. The idea was, instead of having a gravitational wave bop the thing, or make a force on it, was to just look at the distortions directly of this space. In other words, figure out a way that you could measure with a very good meter sticks, better than any you've ever had before, of that 10 to the minus 18 meters. Could you do it? And the idea was to use light, and it's called interferometry. And here's an example of interferometry. So in order for you to understand this is a very stereotyped little picture. This is a laser. It doesn't look like a laser, but that's a laser. And it's going to emit a light beam that goes to this beam splitter, and that beam splitter splits the light. That half of it goes up to that mirror, and then the other half of it gets transmitted and goes to that mirror, and they come back, the light comes back again, part of it goes back to the laser, or it'll go to this screen, which is really a place where you put a photodetector. And I'm going to launch, or this animation will launch now, a beam, and you can watch what's going on. And I just had to tell you that ahead of time. So here's this launching that's going to take place. And wherever you see red, there's light. This is a red light. And these are the actual electromagnetic waves that make up that light. And they bounce back from the mirror. And these wiggly things are the sine waves that make up that light. And you see that there's no light going back. The waves just cancel each other here. That's the way you set this up. And now what will happen is that agency that makes the gravitational waves will move this mirror in and push that mirror out. And you'll notice that light goes to the detector. And just when they're exactly equal in path, then no light goes to the detector. And this is what a detector would see. At this point, when they're equal path lengths, There's no light. The radiation has canceled itself. But when there is unequal path lengths, there is light going to the photodetector. And that is the basic idea of LIGO. There's no more to it than that. I mean, that's the idea. It's not so easy to do. Okay. All right. So then there was now how do you make that idea into an experiment? How do you make that into a real instrument? And that took place, I mean, many ideas were developed by many different people, and I want to walk a little bit through the people. Here is a man who was actually critical to this all. It's a guy named F.E. Pirani, who was at that meeting in Chapel Hill that I described to you. And he was one of the people who said, look, he said, you should be able to see real things from gravitational waves. And the way he was thinking is just set out free masses and watch them move. Watch them move by somehow putting meter sticks or somehow measuring the distance between them. That was his idea, and he showed that that was not going to be dependent on the coordinate system you're using. It was coordinate-independent way of doing it. And that, by the whole business of this coordinate independence, was very important. That was screwing up everything. The fact is that people would do a calculation in one coordinates, and then a different kind of coordinates, they got different answers. And that was part of the trouble in this whole field for years and years, this wonderful idea that you make all your equations coordinate-independent if you can, but somehow you still have to do in the real world, make up coordinates, and they always got you into trouble. So anyway, he proved that you don't get into trouble if you do it right. And here is an idea that was at MIT, was to exploit his idea. And that was to, I won't go through this entirely, but it was the same idea you just saw. We'll talk about it a little more, but here there was laser light coming in, there were masses, and the light was kept bouncing back and forth inside of here. And these masses were not fixed to a table. They were hanging. That was very important that they be free so that they actually could respond to the gravitational wave. And then there's all sorts of stuff to read out this thing that you just saw in that picture. The two ideas that were different here than what was in that simple thing was floating the masses, and the other is bouncing the light back and forth many times. And here's some people. One of them is still with us. All these people are still alive, but this guy is still part of this is David Shoemaker. He's still part of the experiment, and you'll see. And now, the first group that actually picked up on this and did a better job than anybody else was a German group in Munich. This is all of them. And their history is that here's Heinz Billing, who is the director of that group, and he is standing next to a Weber bar, as you can see. And they did a very good experiment to show that, unfortunately, Weber was wrong. And but here's the experiment, and they did that with Frascati. And here are all the people who are working on it. Now, I just want to point out, they then went into this idea and started working on it very hard, and it beautifully showed that it really worked beautifully. And here are the people. And now here is a sad story. This gentleman's 100 now, and he's still around, and Albert Rüdiger is still around, but everybody else has died. And what did they do? They took this idea, and he said, let's make, well, not only use a laser, but we'll use the laser in a better way by putting a mirror between the laser and the interferometer. I'll show you that in a minute. But he and Ron Drever, who is right there, had the same idea about this. He decided that, well, maybe you should modulate the light. He worried about the optics a lot. This gentleman said, let's float all the masses, not just the end masses, float everything. It sounded terribly hard to do, but that was the right thing to do. And then Frau Schnupp had some very elegant ideas of how to do the interferometry. And she was actually the only one who had a physics PhD of the whole group. And she was a mathematical physicist. So this is an interesting group of people. Now, what happened is, so this German group did absolutely stunning work, and right about the same time, Ron Drever in Scotland started a group. He also was working on bars, as the introducer was saying. But he also said, look, what should they do next? And they got into the idea of doing laser interferometry also. And some of it driven by the German group, some of it driven by their own reading of papers and stuff like that. And here's that group, and what do they do? And then these are, they only got, no, he's not alive anymore. Jim Huff is alive. He's alive, but not well. And this guy's now doing work on LISA, which is a thing in space, trying to do this whole thing in space, in a space program. So he developed this technique for angular alignment of all the masses. How do you keep a system with all these mirrors aligned? Brian Mears came up, and he unfortunately died in a mountain climbing accident. He came up with an idea we'll see in a minute, to put another mirror in the system between the detector and the beam splitter, which was a crazy idea, but a wonderful idea. And Jim Huff was the guy who held the group together when Ron left and went to Caltech. So this is the other group. So at the time, in the middle 70s, these were the people who were doing this for the first time. And that's the origin of it all. Now here's what a more modern interferometer, in fact, what we call the advanced detector, looks like as a cartoon. And now so you can identify the pieces that you saw in the animation. Here's the laser, of course. This is a new thing, but here's that beam splitter, and there's that far mirror you saw. So the components that you saw were this, the beam splitter, that far mirror, and that far mirror. And then things were added. And for example, another mirror here to make the light bounce back and forth was there, but this was an idea Ron Drever had, to actually not bounce it around in a circle on the mirrors, but rather have it, these are called Fabry-Perot cavities. The lights are on top of each other. And same thing in here. And you still endeavor to do the same thing. You make it so that the light spends equal time in these two arms, bouncing back and forth, and leaking out of that mirror. And then here, doing the same thing we described before. We'll get to that mirror in a second. And that when you set this up, no light goes to the photodetector. It's that same idea. Except now you have this elaborate system with bouncing. And now come two mirrors that are new, which were not in the other picture. This is the mirror that was invented by both Ron Drever and Roland Schilling. And the idea was, when there's no light going to the photodetector, all the light goes back to the laser. And the idea was, well, why not send that back into the interferometer in such a way that you can build up the power inside the interferometer? And that's what this is called. And you make this mirror so it has a transmission and a position so no light gets back to the laser. So that's called the power recycling mirror. Here's the idea that Brian Mears and also Ron was part of that. They had the idea, which is a much trickier idea. That one's pretty straightforward, it turns out. When you do the arithmetic for this is not so easy. What that does, and I will only tell you that, putting a mirror now between the detector and sort of blocking the light to the detector seems a little crazy. It's not crazy. What it does is it sends only certain kinds of light. The light that has been modulated that has come about because of the wiggling of these mirrors, you can manipulate that light because that gets sent back into the interferometer, and with that you can adjust the spectral response of the interferometer, the different effective sounds that it amplifies, the whole interferometer. So that's a way of changing the property of the interferometer. So quite a subtle and very good idea. So here then is the guts of such a thing. And now I've described to you how you could make a measurement of 10 to the minus 18 meters with a wavelength of 10 to the minus 6 meters. So you're reading a fringe. You're looking at a light, dividing it up somehow by 10 to the 12 parts. That's part of what all that trickery is. But that isn't enough, because you still have to worry about the fact that these mirrors are tied to the ground somehow. And the ground is shaking terrible. The ground is shaking at a micron, 10 to the minus 6, right in this room. You're hopping up and down. You don't feel it by about 10 to the minus 6 meters. I mean, it's just, anybody who's ever looked at a delicate experiment knows. Everything is shaking like mad. So you have to, this is where a lot of the cunning and the technology and the engineering goes. And what are these things? I can't describe everything to you, but this thing that's in front of you here is called the seismic isolation system. I'll describe it to you only in the following idea. How many of you have ever played with these earphones that you take on an airplane that kill the sound of the airplane and you listen to music? The sound killing. Yeah, oh, some of you, okay. Well, that's what the same idea is. You measure what this thing does. That's this thing up here. If you look at it carefully, and when you get to the slides, what it does is it has seismometers in it, things that are sensors of the ground motion, and it has actuators in it that push. And so what the whole idea does, that little piece that's up in the top here and out there, it takes and you measure the ground motion that's at that point, have things that push on the system to kill the ground motion. That's really what it does. So as a feedback system that does that. And it does it 3 times. It does it once out here, and it does it twice inside the vacuum system. And from that system, which now you've killed off the ground noise, you hang, and that's what this thing that's hanging here, this suspension. And that's this. And that's it has 4 pendulums in it, and each pendulum isolates the ground motion more, but also gets rid of some of the thermal noise. This idea was brought to us in advanced Ligo by the group that's part of that's Glasgow's group, the Glasgow group. That was a gift for advanced Ligo. And now here is a more subtle diagram, and Kip will be exploiting this too, so it's worth me explaining a little of it. What it is it's a plot of the noise in the instrument, but what's plotted on the x-axis is the frequency, that's the tone, and along here is the value of h, but as a spectral density. How much at each frequency? How much of h? The noise in h is at each frequency. And you can see here's sort of the performance of the detector. This is not yet there. We'll see in a minute where it really is. And it will have the minimum noise at around 100 hertz, somewhere there. And this is about 10 to the minus 23. So if you want to use this, this is a per bandwidth. So if you talk about 10, your here is about an h of 10 to the minus 22, right in here. So the system can measure 10 to the minus 21 in the region around 100 hertz when it gets really bad at lower frequencies. And then there are various components in here. I'll just pick out the large ones. The thing that's limiting us now is sort of a very interesting, Kip will tell you more about, is the fact that this purple line, that one right there, is the quantum noise in this system. Here is the fact that you're dealing with individual photons. If you increase the power, this will get better. But here, the noise is due to the fact that you're hitting the mirrors with photons, and the mirrors are getting shook around by the photons being hit. You'll get a much better explanation from Kip in his part of this thing. So there, the noise that is dominating us is this one right here, which happens to be the sound waves that are running, the noise in the sound waves that are running in the coatings on the mirrors. Imagine that. Very little tiny coating that's on the mirror. It's not a very good material, and that material is noisy. And it's by the sound waves that run it. So that is the curve, the experimental curve. And, okay. So, this is a little piece of history that's associated with this, is that this is the proposal that was written by all of us, but there's some people you don't know. Here's Robbie Vogt, who was the first director of the project. Prior to this, Kip, Ron, and I tried to run the project, and we failed. I mean, let's be honest about it. And there's Ron. But Ron is a member of this proposal, and so is Kip. There's Kip, and so am I. And there are some people here you don't know. And these are people, the interesting idea that Vogt had was with this very delicate instrument. The thing that was very important was to make sure that the thing didn't get screwed up by the large-scale things that you do to build a facility. So what he did is he coupled engineers and scientists together, at least for the big contracts, like the buildings, the vacuum system, things that were not the subtleties of the interferometer. It was important to get the buildings right and all the large structures right. These are the pairings that were done. These are engineers, and these are this is a scientist, these are the engineers, and I worked with Larry Jones, who we were on the big vacuum system. So that was the original proposal, and it had some very interesting pieces to it. And Kip will remind you of it, but I will remind you of it too. We didn't propose LIGO the way we ran it now. We proposed it in several steps. We proposed it, first of all, right away that there would be 2 sites. You had to have 2 sites. You never could do science without that. And thank God we did that, and they let us do it. Otherwise, as you see in a minute, we couldn't have made a detection that anybody believed. The other thing is that we also broke the thing up into 2 pieces. We said, look, let's use the technology you saw in those prototypes, and we'll make the first detector with that technology. But we told people that we were also going to build another detector, a fancier one, which was the advanced LIGO detector, with a technology we were not quite ready for yet. But we didn't want to start gambling right from the start. It was a big enough gamble to begin with. So initial LIGO was, the whole idea of LIGO was built 2 at once, but in a 2-stage approach, okay? And so now here I'll show you where this sort of led. And these are the same kinds of curves, but you're not going to do much more than me let you point out that this is a sort of a history of what happened. And I'll say sort of right here, these are different curves of noise. This is h of f. Again, frequency dependence of h, and here's the frequency. And you can see here, for example, this is that first red one that goes like that, is the Italian detector, the Virgo detector. I haven't told you about that. That's a detector that's in Pisa, or near Pisa, and that's part of this system that LIGO is part of. And Kip will explain better to you why we need Virgo. But we need many more detectors than just what LIGO has to do the science properly. But so that detector, unfortunately, was not on in the discovery that we will hear about in a minute. The next thing is this is the end of the line with that initial detector. This one here was, this detector right there had a curve that went like that. And it was really quite good at 100 hertz. It went to hell down around here, sort of 50 hertz, and went off the scale. And that was the initial interferometer. That was the first one. And then this is the one that made the discovery, this green one. And it's very much better at low frequencies, as you can see. This is going off scale up there. Virgo was a little better than we were at low frequencies, but this difference between that and this is the reason we made that discovery. And this is now in pretty much the state of that advanced LIGO detector. Now, where should it be? It should be this line. The theoretical lines look very pretty, and of course, the real data never looks that way. But it's this line that's in there, like that, this light blue thing. That's the way we would hope the detector is going to work. With the power we have in it now, we have a problem. We have to solve this. We will. It's just that we're not at our theoretical limit for where we are now. And here, the very bottom curve, this one here, is the one where the design, we come to what we call the design of the interferometer. That's where we'd like to be at the end of the advanced LIGO detector. And there are ideas further after that. But we have to get to that first. And then finally, here's the last curve here is a curve for Virgo. And Virgo's shorter, so they have to do tricky things, but they match the LIGO sensitivity in a critical band. And that's the theoretical curve for Virgo's their advanced detector, okay? So that's the layout of both where we are, you saw where we went, where we began, where we went, where we are, and we hope to be in the short term, not the long term. Kip will talk about the long term. Okay, so here are the two detectors. And these are the ones that these are the two that made the discovery. There's one in Louisiana, in the United States, it's the southern part of the United States, and there's one in the northwest corner of the United States, Ligo, Hanford. And you sometimes hear me say Hanford and Livingston. That's what I'm talking about. And there are, for this, as you'll see, here's what we found. Well, we're not there yet. First, I want to show you a little bit, give you a little tour of the site. Okay, yeah. So this is a very quick view. This is Hanford. This is Hanford again, the beam tubes, and then they will show you. This is Livingston. It's quite different there, quite lush, and these are what the beam tubes look like that contain the beams, and here is a person working on that typical laser table, and we look at the gloves. You have to be very clean. People have to wear masks around that, and this is the control room, and. So that's what you look at when you work at the site. You come and see people working in that place. And here now is a discovery. And quickly go through it with you. What was seen first, these are waves. This is H, this way. 10 to the minus 21 is about there. H of 10 to the minus 21. And these are the real data. This is the data as it arrived in time. Time is this axis. And this axis is time. And this is the actual signal that was seen. And it was seen with a filter, which very much like the filter that you have on a radio. You cut down the noise a little bit at low frequencies. You know, this is a filter function. Low frequencies, you get rid of that. And you cut down the high frequency noise, and that's it. That was sort of the filter that was used to do this. And you saw this wave shape at Livingston, and you saw this wave shape, the blue one, at Hanford, and they're very much the same. Now, what's been done here is this has been moved by 7 milliseconds, because it takes 7 thousandths of a second for the signal to come from Livingston and wind up in Hanford. So that had to be put in. On top of that, you had to flip the signal because of the way that the instruments are laid out. And then there's a theoretical curve that's buried in this thing, which is an analytic curve. And the red curve on here is a curve that Kip will talk about both of these a lot more, namely the fact that the theory, the Einstein theory, actually, when you tell it what, in first order, what masses are doing this and what the things are that you think are doing it, you can get a very good fit between theory and experiment. And here's the residual between the data and the theory. That's the residual. It looks quite white. And the bottom here is a picture of the noise that you hear. If you listen to this, I'm not going to play it for you, but it has a spectrum. This is a spectrum in frequency. Here is middle C right about there. And that's the low end of the piano down in here. So about the range of the piano from the low end to the middle C. And this is the spectrum at Livingston. That's the spectrum at Hanford. So the thing is, we saw the same thing in both places. Not exactly the same because the instruments aren't exactly matched, but this is what it was interpreted as. And what it was interpreted as, and with Kip will tell you a lot more about this, this is flat because it doesn't have that filter function in it, but this is both analytic and theoretical digital data, which predicts this same form. This is the form, and this is what's going on. And Kip will tell you much more, but we knew by just looking at this waveform that these were two black holes. We knew that they were going around each other to make that wave, and then they eventually got closer. This got faster and faster, and then they crashed into each other. and then they made a new black hole. And sort of the amazing numbers are down here. The velocity that they had at the end point was, here's the velocity of light. 0.6 the velocity of light is the fastest. They would crash into each other at almost the speed of, half the speed of light, a little over that. And here's the distance they were apart. That's on this axis over there. So this is quite an impressive thing. I certainly, and many of us, did not believe it when we saw this the first time. It was just too big and too interesting. So so here I just want to show you the data analysis of this. And what's done here is the data analysis of this it was done by cross-correlating the two detectors. In other words, you take the signal from both detectors, plot it together, and multiply them together. And that's being done in this little animation here. And you can see that you're sliding one detector. This is a make-believe. You're sliding this detector over that one. And here's the product, the correlation product. And when they exactly match, you get a kick like that, and that tells you you've seen something. And here is this is the false alarm rate. This is the rate of number of pulses over the time of the experiment versus the signal to noise. The bigger the signal is, the further out on the x-axis you go. And here's that event in that picture, way, way above any of the accidental stuff. Now you do it again, and this is done just by comparing the two detectors against each other. You do it again, and this is the way that we were able to dig out deeper into the signal. And what you're doing now, and let me start this so that I don't waste time. What you do now is you take a calculated signal, which is the thing you see sliding across. It has no noise in it at all. There it is. And you cross-correlate it with the signal and the noise, and you get a thing that's really quite clean. And that found a lot more stuff. The same picture. Again, this is the event rate. This is the signal noise, and it found that same source, but also found some other things. And Kip will talk more about those. And so we had more things to go. And this is a thing, as soon as we announced discovery, this is sort of cute. What happened is I was in New York, I saw this. This is a picture taken by a very good photographer, but this is a sign you see in the subway. It says, scientists can, I can't read it exactly, but you can read it better. I'm at an angle. But scientists can find gravitational waves, but it's much, much harder to find an apartment in New York with a walk-in closet, you see. So, and then this was in the New Yorker in the same week, two birds talking to each other, and was that you I heard? That guy, and oh no, or was it two black holes colliding? So this sort of thing hit the public in a way which was really quite surprising to me. And before I stop, I want to acknowledge two more slides, and that's it. And that is that this is the director of the project when this was all, once the project got going, Barry Barish took over from Robbie Vogt, and he's the one who actually put the system together, got it and built it. And then Stan Whitcomb is a scientist at Caltech who's been part of this project for a very long time. And he was in various guises, both the chief scientist of the project and a deputy director for a while. Here is the actual manager of the project who came with Barry. And here are two people that Barry hired who are actually fundamental to this thing. This is a physicist, Al Lazzarini, and an engineer, Dennis Coyne. And here's the last slide I have. And these are how you'll see the faces get younger and younger. Okay, that's good. And what these this is Peter Saulson, and these are people who are, the LSC is something Kip will describe more to you, but it's a collection of universities, collection of people, collection of institutions that are attached to the LIGO project. It's called the LIGO Scientific Collaboration. And there are many Europeans, there are Asian groups, there are people all over the world that are members of it. And there is a person who is the spokesperson of that person, of that. And the first elected spokesperson was Peter Saulson from Syracuse University. And the second was David Reitze, who is now the current director. And is the current director of LIGO, and here's Gabi Gonzalez, who's the current spokesperson. So these people are the officials within the LIGO Scientific Collaboration, and this is the third director of LIGO, who followed Barry Barish, and David Reitze is now the director. And this group over here is a group of people who I think are absolutely fundamental to the discovery right on the site and worrying about the thing itself. And what are their roles? Dennis, you've met. He's the chief engineer. And David Shoemaker he was at MIT. You saw him before as a boy when he was at MIT. And he is the guy who directed that effort of building the advanced detector. And he was the scientist who was a system scientist, Peter Fritschel, of the detector. And these two gentlemen were the people on site, Valera Frolov and Daniel Sigg, who were at the site doing the commissioning of the detectors. And they were the ones who got them into shape so that they worked. Okay, thank you.